On which side of the screen do you think is work being done? Work is being done only on the left side of the screen, where we see that a block is being pushed across the floor. Even though in the second case, the wooden crate is being pushed, there is no work being done. This is because, in physics, work is said to be done only when an applied force succeeds in moving a body. Consider a wooden block which is at rest on a horizontal surface. When the block is pulled by an external horizontal force F, it is put into motion and is displaced through a certain distance d, and we say work is done on the block. Let's consider a second case, where the direction of the force is not along the direction of the motion of the block. Here, the force makes an acute angle theta with the horizontal. In this case, too, we observe that the block moves in the horizontal direction only. Here, the total amount of force is not being utilized to move the block. Only the component of the applied force along the direction of the displacement is responsible for the motion of the block. This component is F cos theta. Thus, here, the work done on the block by the force is the product of F cos theta and displacement. In this expression for the work done, both F and D are vectors, whereas the product, work done, is a scalar. Thus, this quantity Fd cos theta is called the scalar product of the two vectors F and D. In vector form, it is denoted by a dot in between the two as shown, and is read as F dot D. Hence, it is also referred to as the dot product. Now let's understand dot product in detail. The dot product of two vectors A and B is equal to the product of the magnitude of the two vectors and cosine of the angle between the two vectors. The result of a dot product is always a scalar. Now, let's see some properties of the dot product of vectors. 1. The dot product of vectors is always a scalar quantity. 2. The dot product is commutative. Consider the two vectors A and B inclined as shown. Theta is the angle between the two vectors. The component of one vector in the direction of the other is called the projection of the vector on the other vector, and is denoted by the product of the magnitude of the vector and the cosine of the angle between them. Hence, we see that B cos theta is the projection of vector B on vector A. So, the dot product of vectors A and B can be written as A into B cos theta, which is equal to AB cos theta. Let this be equation 1. Similarly, we see that A cos theta is the projection of vector A on vector B. So, the dot product of vectors A and B can be written as B into A cos theta, which is equal to AB cos theta. Let this be equation 2. From equations 1 and 2, we see that A dot B is equal to B dot A, which is equal to AB cos theta. Thus, the dot product of two vectors is commutative. The dot product obeys the distributive law. So, A dot B plus C is equal to A dot B plus A dot C. All dot products obey the rule M times A dot N times B is equal to Mn times A dot B, where M and N are just constants. Consider the unit vectors along the Cartesian coordinate axis I, J, and K. The angle between any two vectors in the same direction is 0. Thus, when the two vectors are parallel and in the same direction, then the magnitude of their dot products is maximum, as cos 0 degrees is equal to 1. Thus, we get I dot I equals 1, as shown. Similarly, we get J dot J and K dot K equal to 1 as shown. The angle between any two mutually perpendicular directions, that is, between I and J, or J and K, or K and I, is 90 degrees. And cos 90 degrees is 0. So, I dot J is equal to 0. J dot K is equal to 0. And K dot I is equal to 0. How can we find the dot product of a vector expressed in terms of its components along coordinate axis? If two vectors A and B are expressed in terms of their components along coordinate axis AX, AY, AZ, BX, BY, and BZ respectively, then A dot B is equal to AXI plus AYJ plus AZK dot BXI plus BYJ plus BZK, which is equal to AXI dot BXI plus BYJ plus BZK plus AYJ dot BXI plus BYJ plus BZK plus AZK dot BXI plus BYJ plus BZK equal to AXI dot BXI plus AXI dot BYJ plus AXI dot BZK plus AYJ dot BXI plus AYJ dot BYJ plus AYJ dot BZK plus AZK dot BXI plus AZK dot BYJ plus AZK dot BZK, which is equal to AXBX into I dot I plus AXBY into I dot J plus AXBZ into I dot K plus AYBX into J dot I plus AYBY into J dot J plus AYBZ into J dot K plus AZBX into K dot I plus AZBY into K dot J plus AZBZ into K dot K. Substituting the values of I dot I, J dot J and K dot K as 1 and the values of I dot J, I dot K, J dot I, J dot K, K dot I and K dot J as 0 and simplifying, we get A dot B is equal to AX BX plus AY BY plus AZ BZ. It is also equal to BX AX plus BY AY plus BZ AZ, which is equal to B dot A. As the dot product is commutative, A dot B equals B dot A. Now, using the dot product, we can measure the work done as the dot product of the force and displacement, which is equal to FD cos theta. However, the work done can be positive, negative, or zero depending on the values of the angle between the force and the displacement theta. The work done by a force is positive when the angle between force and displacement is acute. That is, the angle is less than 90 degrees. An example of this is when an apple falls freely towards the earth. The work done by the gravitational force on the apple is positive. In this case, the angle between the displacement of the apple and the gravitational force is 0. Similarly, when a spring is compressed, the work done by the compressing force is positive. In this case too, the angle between the direction of the applied force and displacement, which is the compression of the spring, is 0. The work done by a force is negative when the angle between force and displacement is obtuse. That is, greater than 90 degrees and less than or equal to 180 degrees. In the case of a rising balloon as shown, the work done by the force of gravity acting on the balloon is negative, since it is opposite to the displacement of the balloon. In the example of a boy lifting a stone, the work done by the gravitational force on the stone is negative, as the displacement is against the gravitational pull. The work done by a force is 0 when the force is perpendicular to the displacement. Consider a block moved over a horizontal surface. In this case, the displacement is along the horizontal, whereas the gravitational force, which is the weight of the block, acts vertically downwards. Here, work done by the gravitational force is 0, since it acts perpendicular to the displacement of the body. As another example, consider a stone tied to a string, whirled in a circular path. Here, a centripetal force acts on the stone to maintain its circular path. Centripetal force is always directed towards the center of the circular path, whereas the displacement of the stone for an infinitesimal time interval is along the tangent to the circle at the point under consideration. As the direction of the force is perpendicular to the displacement, the work done by a centripetal force is 0. The SI unit of work is joule, which is denoted by the letter J, named after the famous British scientist James Prescott Joule. Thus, 1 joule is defined as the work done on a body when a force of 1 Newton displaces the body in the direction of the force by 1 meter. Now you will learn about the relationship between work done on a body by a net force and the change in its kinetic energy by using the work-energy theorem. According to the work-energy theorem, the work done by a net force on an object is equal to the change in its kinetic energy. We know that the kinetic energy of a body of mass m moving with a velocity v is equal to half mv square. Consider a body of mass m moving with initial velocity u and let the constant net force F act on it. At the end of displacement d, its velocity becomes v. We know from the equations of motion that v square minus u square is equal to 2ad. Multiply both sides with half m and simplifying, we get the expression as shown. We get half mv square minus half mu square is equal to mad. On the left side of the equation, half mv square is the final kinetic energy of the body, and half mu square is the initial kinetic energy. On the right side of the equation, we have the product of m, a, and d. According to Newton's second law of motion, ma is the force on the body. We have on the right side product Fd, which is equal to the work done on the body. This proves that the work done by a constant net force is equal to the change in its kinetic energy. We know that the work done by a force F on a body is W is equal to Fd cos theta, where d is the displacement of the body and theta is the angle between the force and displacement. But in practical situations, a body may be acted upon by a force which may not be constant and is a variable force. A variable force is a force whose magnitude or direction or both vary during the displacement of a body on which it acts. Let's look at an example of a variable force. As the spring oscillates between the extreme positions O and A, the restoring force on it keeps changing with the displacement from the mean position. This is a variable force on the spring. How do we calculate the work done by such variable forces? Let us suppose that a body moves along the direction of a variable force acting on it. We then plot a graph of force F versus displacement x, which helps calculate the varying force with the displacement. The work done by the variable force can be found by calculating the area under the graph. To find the work done by this variable force, we divide the total displacements into n number of small elements or segments: delta x1, delta x2, delta x3, and so on till delta xn. The work done with respect to the first segment, delta x1, is the area of this first segment, that is, F1 into delta x1. Work done with respect to the second segment, delta x2, is the area of the second segment, that is, F2 into delta x2. For the third segment, delta x3, work done is the area of the third segment, that is, F3 into delta x3, and so on. Here, we assume that the force remains constant for each small segment. Thus, the area of any segment will be denoted by the expression delta A is equal to Fx delta x. Let this be equation 1. The total work done is equal to the sum of the areas of all the small elements, which is equal to the summation of F delta x taken within the limits from x1 to xn, as in expression 1. If the size of each segment is very small, each segment tends to 0, and we have a large number of such segments. And the total work done is calculated as W is equal to sigma of F delta x between the limits x1 to xn, as the limit of x tends to 0. Let this be equation 2. Hence, the work done for a varying force can be expressed in integral form, as W is equal to integral f dx in the limits x1 to xn. Let this be equation 3. We know that according to the work energy theorem, the work done, W, by a net force on a body is equal to a change in its kinetic energy, Ke, as in expression 4. W is equal to delta Ke. Let us now try to prove the work energy theorem for a variable force. We know that the work done by a variable force can be found by the expression W is equal to integral f dx in the limits x1 to xn. Let's call this equation 5. If the velocity of the object at an instant is v, then its kinetic energy at the instant is expressed as half mv square. Let this be equation 6. On differentiating equation 6 with respect to time t, we get the rate of change of kinetic energy as dk by dt is equal to d by dt of half mv square. Thus, on simplification, we get dk by dt is equal to half m d by dt of v square. On further simplifying, we get dk by dt is equal to half m into 2v dv by dt. Thus, dk by dt is equal to mv dv by dt. This can also be written as dk by dt is equal to mdv by dt into v. On the right side of the equation, we know that dv by dt is the rate of change of velocity, which is the acceleration of the body. Thus, we get dk by dt is equal to mav. However, according to Newton's second law, F is equal to ma. Therefore, we get dk by dt is equal to fv. Also, the velocity term v in the expression can be represented as the rate of displacement v is equal to dx by dt. Hence, we get expression 7 as shown, which is dk is equal to f dx. Integrating expression 7 in the limits from x1 to xn for the displacement and for k1 to kn for the corresponding kinetic energy, we get integral dk within the limits k1 to kn equal to integral f dx within the limits x1 to xn. The left side of the equation indicates the change in kinetic energy, and the right side of the equation indicates the work done on the body by the variable force. Thus, we see that the work done by a variable force on a body is equal to the change in kinetic energy of the body. This proves that the work energy theorem holds true for a variable force. Now let us learn about potential energy. The energy stored in a body by virtue of its position or configuration is called potential energy. Consider a body of mass m placed on the surface of the earth. The weight of the body placed on the surface of the earth is denoted by mg. Let this be equation 9. To raise the body through height h above the surface, the minimum force required is its weight, which is equal to mg. Consider the upward direction to be positive. The work W done to raise the body through height h against the gravitational force of attraction by an external force is mgh. Let this be equation 10. This work is stored in the body as its potential energy. The gravitational potential energy of the body as a function of height h is denoted by V of h, and it is the negative of work done by the gravitational force while raising the body through the height. Thus, we have V of h is equal to mgh. If h is the variable, it can be easily shown that the gravitational force F is equal to the negative of the derivative of V of h with respect to h. Thus, F is equal to minus d by dh of Vh equal to minus d by dh of mgh, which is equal to minus mg. Let this be equation 11. The negative sign indicates that the gravitational force is directed downwards. Hence, when released, the body comes down with increasing speed, converting its potential energy into kinetic energy. The body strikes the ground with the velocity v denoted by the expression v square is equal to 2gh. On multiplying both sides of the above equation with half m, we get half mv square is equal to half m into 2gh, which is equal to mgh. The left side of the equation is the kinetic energy of the body on reaching the ground, and the expression on the right is the potential energy stored. Thus, this proves that the potential energy of the body is transformed into its kinetic energy when the ball is released. Hence, physically the concept of potential energy is applicable to the type of forces where work done against the force is stored in it. Mathematically, the potential energy V of x is defined for any force F of x, which can be written as F of x is equal to minus dV by dx, shown by expression 12. Integrating on both sides of the expression within the limits of initial position xi and final position xf. And on simplifying, we get minus of Vf minus Vi. On further simplification, we can arrive at the conclusion as shown in equation 13. Integral of fx dx within the limits xi and xf is equal to Vi minus Vf. From equation 13, we can see that the work done on a body by the force depends on the initial and final positions only, and not on the path followed by the body. Such a force is called a conservative force. By definition, If the work done by a force is independent of the path followed, then it is a conservative force. Such a force is characterized by equation 13. Gravitational force and elastic force, in the case of a stretched spring, etc., are examples of conservative forces. Let's try to understand these forces. We see that when a box is dropped from a certain height, the work done by gravity on the box is mgh. When the same box slides down the smooth inclined plane at an inclination of theta with the horizontal, the force acting down along the incline is mg sine theta. The distance travelled by the box is L. And hence, the work done by gravity on it is denoted by the expression W is equal to mg sine theta into L. On simplifying, we get work done as mgh as shown in expression 15. So far, we have studied conservative forces. Let us now learn about non-conservative forces. If the work done by a force depends on the path followed, it is a non-conservative force. For example, friction is a non-conservative force. Consider a box placed on a rough surface and moved through different positions A and B in different paths. In the first case, the box is moved along a straight path from A to B as shown. In the second case, the box is moved along a zigzag path from A to B as shown. The distance travelled is different in both cases. Hence, the work done to overcome the friction in both cases is different and is dependent on the path followed. Thus, friction is a non-conservative force. Consider a body of mass m. The sum of kinetic energy, K, and potential energy, V, possessed by the body is called the total mechanical energy of the body. Let this be equation 1. If a body is displaced due to a conservative force F, which is a function of displacement x, then from the work energy theorem, the gain in kinetic energy is related to the work done by such a conservative force F of x and is denoted by the equation delta K is equal to F of x into delta x. Let this be equation 2. Let's now look at the relationship between this conservative force and potential energy. Let delta V be the change in potential energy. As f of x is equal to the negative of delta V by delta x, we get delta V is equal to minus f of x delta x. Let this be equation 3. Equation 3 expresses the relationship between a conservative force f of x and potential energy V of x. We know that mechanical energy is the sum of kinetic energy and potential energy of a system. So, by adding equations 2, delta K is equal to f of x into delta x, and equation 3, delta V is equal to minus f of x delta x. We get delta K plus delta V is equal to f of x delta x minus f of x delta x. Thus, delta K plus delta V is equal to 0. In other words, we can say that delta of K plus V is equal to 0. Let this be equation 4. Since delta of K plus V is the total mechanical energy, we can say from equation 4 that the change in total mechanical energy is 0 for a system all along its path. This is the principle of conservation of mechanical energy, which states that the total mechanical energy of a system is conserved if the forces doing the work on it are conservative. Let's now understand the principle of conservation of mechanical energy. Consider any 2 points A and B in the path of a body falling freely from a certain height h. According to the principle of conservation of mechanical energy, we can say that for points A and B, the total mechanical energy is constant in the path travelled by a body under the action of a conservative force. That is, the total mechanical energy at A is equal to the total mechanical energy at B. Or KEA plus V of x for A is equal to KEB plus V of x for B. Let this be equation 5. From the above discussion, we observe that work done by a conservative force is path independent. It is equal to the difference between the potential energies of the initial and final positions and is completely recoverable. Also, as the work done by a conservative force depends on the initial and final position, we can say that work done by a conservative force in a closed path is 0, as the initial and final positions in a closed path are the same. Let's understand this with an example. Let's throw a body vertically upwards. In this example, we assume that the potential energy is only due to gravitational force, and we take the ground level as the reference level. The body thrown vertically upwards with velocity u has only kinetic energy at A and 0 potential energy at A. Its total mechanical energy is expressed by half mu square. Let this be equation 6. At point B, the body possesses both potential and kinetic energies. The potential energy is mgx and the kinetic energy is half mv1 square, where v1 is the velocity of the body at position B. Total mechanical energy at B is denoted by equation 7. Using the equations of kinematics, we get v1 square minus u square is equal to minus 2gx. Simplifying, we get the expression for v1 as v1 square is equal to u square minus 2gx. Let this be equation 8. Now substitute equation 8 in equation 7. And upon simplifying, we get total mechanical energy at B equal to half m into u square minus 2gx plus mgx, which is equal to half mu square minus half m into 2gx plus mgx, equal to half mu square minus mgx plus mgx. Thus we get the total mechanical energy at B equal to half mu square. Let this be equation 9. When the body reaches point C, that is, the maximum height, it has only potential energy and 0 kinetic energy as the velocity at this point v is 0. Its total mechanical energy at c, denoted by mgh. Let this be equation 10. We learnt earlier that the maximum height h reached is denoted by the expression u square by 2g. Let this be equation 11. Substituting equation 11 in equation 10, we get the total mechanical energy at c is equal to mg into u square by 2g. And on simplifying, we get the total mechanical energy at c is equal to half mu square. Let this be equation 12. We see from equation 6, 9 and 12 that the total mechanical energy at all points along the path of the body is the same. Hence, mechanical energy is conserved at all points along the path. Now let's look at another example. The individual on the bike shown revolves in a vertical circle of radius r. The individual along with his bike is considered to be a system. We assume that the potential energy is only due to gravitational force, and we take ground level as the reference level. At its lowest point, which is taken as the reference level, the bike possesses only kinetic energy but no potential energy. Let it be assigned a horizontal velocity u at the lowest point A. At point A, the total mechanical energy of the system is denoted by the expression half mu square. Let this be equation 13. When it is at horizontal position C, its velocity is v1, and the height of C from the reference level is equal to r. When at C, its total mechanical energy is partly kinetic, which is half mv1 square, where v1 is the magnitude of velocity at C, and partly potential, which is mgr. The total mechanical energy at C is denoted by half mv1 square plus mgr. Let this be equation 14. When it reaches the highest point B, it has velocity v, and its height with respect to the reference level is 2r. It has maximum potential energy, which is mg into 2r, and least kinetic energy, which is half mv square. The total mechanical energy at B is denoted by half mv square plus mg into 2r. Let this be equation 15. As the individual moves on the bike, which is together considered a system, in the circular path, a centripetal force Fc, denoted by mv square by r, acts on the system. At position B, weight mg and normal force Fn provide the necessary centripetal force. When the speed at position B is decreased, the centripetal force decreases, and hence the normal force. To complete the motion along the circular path, the speed at B should be minimum such that the normal force on the bike is 0. Thus, mv square by r must be provided by mg, which is denoted by equation 16. Simplifying for v square, we get v square is equal to gr, or V is equal to the square root of GR. Let this be equation 17, which indicates the minimum velocity at B required to complete one revolution of the vertical circular path. According to the principle of conservation of mechanical energy, the total mechanical energy at A is equal to the total mechanical energy at B. Thus, half mv square plus mg into 2r is equal to half mu square. But since v squared is equal to gr, substituting the minimum velocity at point B, v is equal to the square root of gr in equation 15. We get half mgr plus mg into 2r is equal to half mu square. On further simplification, we get half mg into r plus 4r is equal to half mu square. Thus, we get u square is equal to 5gr, or u is equal to the square root of 5gr, where u is the projection velocity at A. Let this be equation 18. Thus, from the earlier examples, we see that according to the principle of conservation of mechanical energy, energy can neither be created nor destroyed. It can only be transformed from one state to another. Consider a block attached to a spring placed on a smooth horizontal surface. The other end of the spring is attached to a rigid wall. The position at which the spring is at rest initially is considered to be the mean position, with no displacement of the spring. Then, the spring is compressed and released. You can observe the spring oscillating to and fro from the rest or mean position. The displacement of the block is always measured from the mean or rest position. The spring here is under the action of a variable force, known as the spring force, which always acts towards the mean position or in the opposite direction to the displacement. When the spring is stretched, the displacement is positive. When the spring is compressed, the displacement is negative. The spring force is the restoring force which is responsible for bringing the block attached to the spring back to its mean position. The spring force F is directly proportional to the displacement x from the mean position. Thus, we see that the spring force F is proportional to minus x. We say minus x as the spring force is always directed opposite to the direction of displacement. Or, spring force F is equal to minus kx, where k is the spring constant. Let this be equation 1. In equation 1, F is equal to minus kx, which represents the force law for the spring known as Hooke's law. Work done W by the spring force is denoted by the expression integral F dx in the limits 0 to xm, where xm is the maximum displacement of the spring. Let this be equation 2. Since the spring force F is equal to minus kx, we get W is equal to minus integral kx dx in the limits 0 to xm. Let this be equation 3. On integrating equation 3, we get W is equal to minus k into x square by 2 in the limits 0 to xm. Thus, we get the work done by the spring force equal to minus half kxm square. Hence, the work done by the external elongating force will be plus half kxm square. This is the work done by the external elongating force against the spring force, and hence is stored as potential energy in the spring, as given by equation 4. Work done by the spring force can also be calculated by the area covered under the graph of displacement x during elongation or compression taken on the x-axis and the corresponding spring force F taken on the y-axis. The area of the shaded portion indicates the work done by the spring force. In equation 3, W is equal to minus integral kx dx in the limits 0 to xm. We know that the initial displacement is 0 and the final displacement is xm. Instead, if the initial displacement is x1 and the final displacement is x2, then the work done W by the spring force would be equal to the negative of integral kx dx in the limits x1 to x2. Let this be equation 5. Then the work done by the spring force will be equal to half kx1 square minus half kx2 square. Let this be equation 6. Equation 6, where W is equal to half kx1 square minus half kx2 square, indicates the work done by the spring force. Then the work done by the external force W will be equal to half kx2 square minus half kx1 square. Let this be equation 7. Now if the spring is compressed to x2 and brought back to x1, then the work done by the spring force according to equation 7 will be half kx1 square minus half kx1 square, since the final position is the same as the initial position. Then the work done will be equal to 0 as in equation 8. This proves that the spring force is a conservative force since the work done for a closed path or round trip is 0. Thus, we define the potential energy V of x of the spring as 0 when the system of the block and the spring is in equilibrium position. For any extension or compression x of the spring, we have V of x is equal to half kx square. Taking the derivative of the equation of potential energy of the spring, we get minus d by dx V of x is equal to minus d by dx half kx square. On further simplification, we get f of x is equal to minus half k into dx square by dx. Thus, by doing the derivation of the equation of potential energy of a spring, we can easily verify the equation for the spring force as f of x is equal to minus kx as shown. According to the work energy theorem, the work done by a net force on an object is equal to the change in its kinetic energy. That is, F delta x is equal to delta k, where F is the net force, delta x is the displacement, and delta k is the change in kinetic energy. Let this be equation 9. Now, if the forces acting on the body include both a conservative force Fc and non-conservative force Fnc, then the equation 9 can be written as Fc plus Fnc delta x is equal to delta k. Let this be equation 10. Simplifying, we get Fc delta x plus Fnc delta x is equal to delta k. Since Fc delta x is equal to minus delta v in equation 10, we get minus delta v plus Fnc delta x equal to delta k. Let this be equation 11. We have Fnc delta x equal to delta of k plus v. Let this be equation 12. Since k plus v is the total mechanical energy of the body, which is the sum of the kinetic and potential energy of the body, equation 12 shows that the work done by the non-conservative force is equal to the change in the total mechanical energy of the body. Some forms of energy that we will deal with in this module are heat energy, chemical energy, electrical energy, and nuclear energy. Now, let's understand heat energy first. When satin cloth pieces are rubbed against each other, due to friction, sufficient heat is produced to make the hands feel a rise in temperature. The rise in temperature is due to the rise in internal energy of the body. Here, the satin cloth pieces. Consider that a body is given a push and is then released. When it comes to rest, all its kinetic energy is lost, and a part of this kinetic energy is converted into heat, and the remaining is lost in doing work against the friction. To overcome friction, there is a slight rise in the temperature of the surfaces in contact. Let us look at another form of energy, chemical energy. Chemical energy is produced when the molecules of the reactants participating in a chemical reaction combine to attain greater stability by forming stable compounds. The burning of any form of fuel is a chemical reaction. Burning is an exothermic chemical reaction where the chemical energy of the reactants is mainly converted into heat energy, which can later be manifested in other forms. Thus, in an exothermic reaction, the energy of the reactants is greater than that of the products. Hence, exothermic reactions like combustion of fuels are indispensable in catering to our daily energy needs. There are some other chemical reactions that absorb heat during their reaction and are called endothermic reactions. Some reactions, such as photosynthesis, are endothermic reactions which allow plants to make sugar from carbon dioxide in the presence of air. Chlorophyll acts as a catalyst in the process of photosynthesis. In this case, the energy required for the reaction comes from sunlight. Now, let's understand electrical energy. Electricity is the most convenient form of energy. Electricity is a manifestation of electrical energy and is responsible for running many of the devices in our daily lives, such as electric bulbs, fans, grinders, etc. Till the late 19th century, physicists were of the view that the mass of an isolated system remains constant and it is conserved. They believed that matter can be neither created nor destroyed. It can only change from one form to another. For example, when water is frozen, it turns to ice. The ice melts to water, and when water is heated, it turns to vapor. In all the three forms, the mass of the system remains the same. However, Albert Einstein proposed his famous mass-energy equivalence relation. E is equal to mc square, to show that mass and energy are equivalent. In this relation, E is equal to mc square, and c is the speed of light in vacuum, which is approximately 3 × 10⁸ meters per second. Thus, according to Einstein's mass-energy equivalence relation, mass and energy are equivalent to each other. Mass can be converted into energy and vice versa. When a mass m is destroyed completely, the equivalent energy E is produced. Thus, according to Einstein's mass-energy equivalence equation, 1 kilogram of matter can produce a humongous amount of energy, which is E is equal to 1 × 3 × 10⁸ square joules, equal to 9 × 10⁻16 joules of energy. The energy produced by 1 kilogram of mass is equivalent to the annual electrical energy produced by a power generating station, that is 3000 megawatts. Now, if 1 gram of mass is completely destroyed, the energy produced is expressed as E is equal to mc square, that is equal to 0.001 × 9 × 10⁻16, that is equal to 9 × 10⁻13 joules. One of the most expensive forms of energy is nuclear energy. Nuclear energy is energy derived from a nuclear reaction, such as nuclear fusion or nuclear fission, from which energy may be released in accordance with Einstein's mass-energy equivalence relation. In nuclear fission, a heavy nucleus like uranium-235 absorbs a slow neutron and hence splits into lighter nuclei. The final mass of products is observed to be less than the total mass of the reactants, and this difference in mass is known as mass defect, denoted by delta M. The mass defect delta M is converted into energy in accordance with E equal to delta M into c square. In a nuclear fusion reaction, lighter nuclei fuse to form a heavier nucleus. This fusion is accompanied by the release of a large amount of inherent energy in accordance with the mass-energy equivalence relation. In nuclear fusion too, there is a mass defect which accounts for the amount of energy released according to E is equal to delta M into C square. The source of the massive amount of energy released by the Sun and the stars is believed to be due to a nuclear fusion reaction, when isotopes of hydrogen, namely deuterium and tritium, undergo fusion to form an isotope of helium and a neutron with the release of a large amount of energy. The energy released is due to the conversion of a mass defect between the reactants and products in the reaction. The law of conservation of energy states that the total energy of an isolated system is always conserved and that energy can only be transformed from one form to another, but can neither be created nor destroyed. For example, when a firecracker explodes, the chemical energy stored in it is converted into light, heat, and sound energy. Nuclear energy is used to produce electrical energy in a nuclear reactor. Different forms of energy are used to do work. Earlier, we learned that work is said to be done when a force F acting on a body displaces the body through D in the direction of the force. When work is done, energy is transferred. The rate at which work is done or energy is transferred is called power. Thus, power P is equal to work done W by time T. Instantaneous power P is equal to dW by dt. But dW is equal to F dot dr, where dr is the displacement. Therefore, P is equal to F dot dr by dt, which is equal to F dot V, since dr by dt is equal to instantaneous velocity v. Power is a scalar quantity and its SI unit is watt, and its dimensional formula is m power 1, L power 2, T power minus 3. Power can be expressed in horsepower denoted as HP, and 1 horsepower is equal to 746 watts. The commercial unit of electrical energy is kilowatt hour denoted as kWh. 1 kilowatt hour is equal to 1000 watt into 1 hour, and which is equal to 1000 watt into 3600 seconds, and is equal to 36 into 10 to the power 5 joules. We come across many types of collisions between different bodies in our daily lives, like the collision between a bat and ball, and the collision between a striker and coins in a game of carom. In the subatomic world, we find collisions between various subatomic particles. For example, a subatomic particle called a neutrino collides with another subatomic particle, a neutron. The neutron disappears and one finds a proton and an electron as products of this collision. In any collision, the linear momentum of the system is conserved. If we consider one-dimensional collision between two bodies, then from Newton's third law of motion. They experience equal and opposite forces, F12 and F21, on each other, such that F12 is the force on the first body due to the second, and F21 is the force on the second body due to the first, and F12 must be equal to minus F21. From Newton's second law of motion, if delta P1 and delta P2 are changes in momenta of the first and second bodies respectively, then force F12 will be equal to delta P1 by delta T, and force F21 will be equal to delta P2 by delta T. Since F12 is equal to minus F21, this implies that delta P1 by delta T is equal to minus delta P2 by delta T. Therefore, delta P1 is equal to minus delta P2, or delta P1 plus delta P2 is equal to 0. Hence, we can say that the total change in momentum during a collision is 0, or we can say that the total momentum of the system is conserved during collisions. There are three different kinds of collisions: elastic collision, inelastic collision, and completely inelastic collision. In a collision, if both the total momentum P and total kinetic energy Ke of the colliding bodies is conserved, then it is an elastic collision. In such a collision, the bodies move separately after the collision and the loss in kinetic energy delta Ke is 0. This implies that there is no loss in kinetic energy. For example, the collision between subatomic particles is an elastic collision. In a collision, if only the total momentum of the colliding bodies is conserved and not the kinetic energy, and the colliding bodies move separately after the collision, then the collision is called an inelastic collision. There is some loss in kinetic energy of the system during this collision. This implies that delta Ke is not equal to 0. For example, the collision between billiard balls is an inelastic collision. In a collision, if only the total momentum of the colliding bodies is conserved and the total kinetic energy is not conserved, and the bodies stick together after the collision, then it is a perfectly inelastic collision. There is a maximum loss of kinetic energy during this collision. This implies that delta Ke is maximum. For example, the collision between a clay ball and a metallic ball is a perfectly inelastic collision. Consider a head-on collision, that is, one in which the velocities of the bodies before and after the collision are along the same straight line. The mass of the first body is m1 and is moving towards right with velocity u1. The mass of the second body is m2 and is also moving towards the right with velocity u2, such that the two bodies are moving along the same straight line. If u1 is greater than u2, then there will be a collision between the two bodies. Let the collision between the two bodies be elastic, which implies that it is a completely elastic collision. Let the velocity of m1 be v1 and that of m2 be v2. just after the elastic collision. Since the momentum is conserved, we have m1u1 plus m2u2 is equal to m1v1 plus m2v2. On rearranging the terms and simplifying, we get m1 into u1 minus v1 is equal to m2 into v2 minus u2. Let this be equation 1. Since the total kinetic energy is also conserved in an elastic collision, we have half m1u1 square plus half m2u2 square is equal to half m1v1 square plus half m2v2 square, or m1u1 square plus m2u2 square is equal to m1v1 square plus m2v2 square. On rearranging the terms and simplifying, we get m1 into u1 square minus v1 square is equal to m2 into v2 square minus u2 square. On further simplifying, we get m1 into u1 minus v1 into u1 plus v1 equal to m2 into v2 minus u2 into u2 plus v2. Let this be equation 2. Now, dividing equation 2 by equation 1 and simplifying, we get u1 plus v1 minus u2 is equal to v2. Let this be equation 3. Substituting value of v2 from equation 3 in equation 1 and simplifying as shown. We get final velocity of m1 as v1 is equal to m1 minus m2 by m1 plus m2 into u1 plus 2m2 by m1 plus m2 into u2. Let this be equation 4. From equation 3, we get v1 is equal to v2 plus u2 minus u1. Let this be equation 5. Substituting the value of v1 from equation 5 in equation 1 and simplifying as shown, we get final velocity of m2 as v2 is equal to m2 minus m1 by m2 plus m1 into u2 plus 2m1 by m2 plus m1 into u1. Let this be equation 6. As a special case, if we assume that m2 was at rest before the collision, then u2 will be 0 and v1 reduces to v1 is equal to m1 minus m2 by m1 plus m2 into u1. Let this be equation 7. And v2 is equal to 2m1 by m2 plus m1 into u1. Let this be equation 8. Moreover, in this case, if m1 is equal to m2, say equal to m, then we get v1 is equal to 0 and also v2 equal to u1. Thus, we see that the two bodies exchange their velocities after the collision. If m1 is much greater than m2, then we neglect m2 in equations 7 and 8. Thus, we get v1 from equation 7 equal to u1. And also, we obtain v2 from equation 8 equal to 2u1. Therefore, in such a case, we see that m1 continues to move with the same velocity as it had before the collision, whereas m2 now acquired double the initial velocity of that of m1. In a real-life situation, we do not encounter collisions where bodies before and after colliding move along the same straight path. They collide in two dimensions, as usually observed in a game of billiards or carom. Consider an elastic collision in two dimensions, where a body of mass m1 with velocity u1 along the x-axis collides elastically with a body of mass m2 at rest. This implies that the velocity of m2 before collision, u2, is 0. Just after the collision, m1 moves away with velocity v1, making a positive angle alpha with the x-axis, and m2 moves away with velocity v2, making a negative angle beta with the x-axis. Since the collision is elastic, the total momentum and total kinetic energy of the system must be conserved for the bodies. The law of conservation of momentum must be applied both along the x-axis as well as the y-axis. v1 cos alpha and v2 cos beta are the components of v1 and v2 respectively along the x-axis. Hence, according to the law of conservation of momentum applied along the x-axis, we get m1u1 plus m2u2 is equal to m1v1 cos alpha plus m2v2 cos beta. And on simplifying, we get m1u1 is equal to m1v1 cos alpha plus m2v2 cos beta. Let this be equation 9. v1 sin alpha and minus V2 sine beta are the components of V1 and V2 along the positive y-axis and the negative y-axis respectively. Hence, according to the law of conservation of momentum applied along the y-axis, we get m1u1 plus m2u2 is equal to m1v1 sine alpha minus m2v2 sine beta. As the initial velocities of the two bodies along the y-axis are 0, we get 0 on the left side of the equation. And thus, we get 0 is equal to m1v1 sine alpha minus m2v2 sine beta. On further simplification, we get m2v2 sine beta is equal to m1v1 sine alpha. Let this be equation 10. Since the total kinetic energy is also conserved in an elastic collision, and as u2 is 0, we have half m1u1 square is equal to half m1v1 square plus half m2v2 square. On simplifying, we get m1 into u1 minus v1 into u1 plus v1 is equal to m2v2 square. Let this be equation 11. The total quantities among the three equations are m1, m2, u1, alpha, beta, v1 and v2. Thus, there are 7 quantities and 3 equations. By knowing the values of m1, m2, u1 and at least one among alpha or beta, we can determine the values of v1 and v2. Now, consider a head-on collision, that is, one in which the velocities of the bodies before and after the collision are along the same straight line. That is, a one-dimensional collision. A body of mass m1 moving with velocity u1 collides with another body of mass m2 moving with velocity u2 in the same direction along the same straight line. Let the collision between m1 and m2 be completely inelastic. As the collision is completely inelastic, they stick together after the collision and move with a common velocity v. Since the momentum of the system is conserved during the collision, we have m1u1 plus m2u2 is equal to m1 plus m2 into v. This implies that the velocity after the collision v is equal to m1u1 plus m2u2 divided by m1 plus m2. Let this be equation 12. The loss in kinetic energy of the system, delta Ke, is equal to the kinetic energy before the collision minus the kinetic energy after the collision, which is half m1u1 square plus half m2u2 square minus half into m1 plus m2 into v square. We substitute the expression for the common velocity v from equation 12 in the expression for delta Ke and simplify as shown. for convenience, we mark two expressions, A and B, and simplify them separately as shown. Thus, the loss in kinetic energy in a completely inelastic collision is as shown on further simplification. As half m1 m2 by m1 plus m2 into the square of u1 minus u2. Let this be equation 13. In case the second body of mass m2 is at rest before the collision, we have u2 is equal to 0 and then the loss in kinetic energy is equal to half m1 m2 u1 square by m1 plus m2.